Hello and welcome back to MylesMaths. Today we're going to be looking at iteration, and we're going to look at defining iteration, learn how to derive an iterative formula, be able to determine if there is a root, that is a solution between two particular x values, be able to use an iterative formula to approximate a solution to a cubic function, know the limitations of iteration, and to learn why we actually learn this in the first place. Let's, to begin with, look at something a bit more familiar than a cubic. Let's look at a quadratic. So here we have a quadratic equation, and here we have the two solutions of the quadratic equation. That is the roots, the points at which the equation crosses the x-axis. And we know that we could solve a quadratic equation in a variety of ways. We could look to factorize it. This particular quadratic won't factorize, unfortunately. We could use the quadratic formula. We could complete the square, which would be slightly awkward. You'd end up with x plus 2.5 all squared, which you've then got to work out the square of 2.5. If you don't know that, you're a bit stuck with this. And we could use, of course, iteration. Now, iteration's a little bit of a sledgehammer to crack a nut with a simple equation like this, because you'd probably go with quadratic formula. However, let's look at how we do it. So to begin with, we would derive an iterative formula. Now, iteration is about a repetitive system using a formula. So let's derive the formula first, and then I'll show you the iterative system, repeating system. So here's the original equation that we're going to solve. And what we're going to do is we're going to rearrange this to get x equals. We're going to do, in fact, all the things we've ever told you not to do. So to begin with, we're going to take x squared off both sides. We're going to add 7 to both sides. We're going to get 5x equals 7 minus x squared. And from there, we're going to divide by 5 and get x equals 7 minus x squared over 5. Now, this is not an iterative formula. However, an iterative formula relies on us picking a value for x here and using that in that formula to generate a new value for x, which we then use back here to generate another new value of x, which we then use back here to generate another new value of x. We call the initial value of x that we use x0. And x0 will produce x1 and so on. So we label it up as an iterative formula like this, so that xn will generate the next value, which will be xn plus 1. So if n was 0, then this one would be x1. If n here was 10, we'd have x10. This would be x10 plus 1. 10 plus 1 is 11. So this is whatever iteration this is one more than it. So let's look at how we would use this. If we're going to solve this particular equation, we're going to pick an initial value of x0 equals 1. We call it x0 because it's the initial value, and we haven't done any iterations. So on our first iteration, x1 will be 7 minus x0 squared divided by 5, and x2 will be x1 squared, or 7 minus x1 squared divided by 5, and of course x3, I guess you're there ahead of me, will be 7 minus x2 squared divided by 5. So the number here is just the number of the iteration, 0, 1, 2, and so on. So let's have a look at what that looks like when we put some numbers in. I'm starting with x0 equals 1, so x1 must be 7 minus 1 squared over 5, which is 1.2. I'm then going to substitute 1.2 into the formula and get 7 minus 1.2 squared over 5, which gives me 1.112. I substitute 1.112 into the formula, which gives me 1.152, and so on. And after 4 iterations, I've got 1.134. Now, if I continue this process, by the time I get to the 9th and 10th iterations, I find that they're 1.140 something and 1.140 something. Clearly, they're not quite the same past the 3rd decimal place. However, to 2 decimal places, I can see this is 1.14. If I have a look at the equation, the actual graph, I can see here that if I look very carefully, this is 5, so this must be 1, and that point at which that crosses the x-axis there must be just about 1.1. So I can see this looks right with my graph. However, I might notice that I've only generated one of the possible routes. I haven't got the other route. And this is the first sort of limitation of iteration. It only produces one particular route at a time. If I'd done this using the quadratic formula, of course, I would have got both routes out, and I would have done considerably less work in order to generate both the 1.14 route, which we can see is correct, 2 decimal places, and I'd have got the other route as well, the minus 6.14 route, which you could see here. So why use iteration at all? Well, the reason we use it is because when you have a cubic such as this, there isn't a cubic formula in the same way there's a quadratic formula. There isn't a simple formula that you can use to get a solution to a cubic equation. So iteration is a method of doing this. And here with this particular cubic, I've got 3 possible routes that I could find. So what we're going to do is we're going to look at x cubed minus 3x plus 1 equals 0. We're going to show that it has a root between 0 and 1. We're then going to derive the iterative formula. Now, they won't ask you at GCSE to just come up with an iterative formula. They'll give you it, and they'll ask you to show how it could be derived. So it's all about your method of doing it, showing you all you're working out. And then we're going to generate an approximate solution to the equation after 5 iterations, assuming that x0 equals 1. So the first thing we're going to do is we're going to show that this has a solution between 0 and 1. And the way we're going to do that is just by taking y equals x cubed minus 3x plus 1. And we're going to plug the 2 values that we're given for x in, 0 and 1. And we're going to substitute those in. So if we substitute in x equals 0, we find that y actually equals 1. And if we substitute x equals 1 into this, we find that y equals 1 cubed minus 3 times 1 plus 1, which is minus 1. Now, these correspond to 2 points on the graph, so it's worth going back and looking at this. When x was 0, we could see that y would have been 1. And when x was 1, we could see that y was minus 1. And therefore, to get from this point down to this one, I had to cross the x-axis, and that means there had to be a route between those 2 values. So if I look at this without the graph, I can see that here I was, when x was 0, I had a positive value, and when x was 1, I had a negative value, and it's this change of sign. And it can be positive to negative or negative to positive, it doesn't matter which, but it will tell you that if it changes sign, it must have crossed the x-axis in between. And then I give a little explanation of this. Hence, as the line crosses the x-axis between 0 and 1, there must be a solution in this range. So I can see that there is a solution between x equals 0 and x equals 1 without actually drawing the graph. Part B of the question says, show the following iterative formula can be derived from x cubed minus 3x plus 1 equals 0. So what I'm doing here is I'm again, as I did in the previous exercise, just trying to get x equals. And I can see quite easily from the final form that I'm going to end up with down here that I need to have, I need to be dividing by 3 at some point. So if I'm going to be dividing by 3, I'll make it 3x equals. So I add 3x to both sides in this case to get a 3x here. Obviously the 3x just disappears out of here, these two cancelling out. I'm then just going to divide by 3 so that I'm dividing this 3x by 3 to get x. And this gives me 1 plus x cubed over 3 equals x. So to turn that into an iterative formula, you'll notice here I've just reversed this. I've put left to right and right to left. However, my xn becomes the thing which is kind of part of the formula, and the xn plus 1 becomes the subject of the formula. So, and that's the same every time you do this. So I've now got my iterative formula. I've now got to go and show that I can get a solution to my iterative formula. So I know that x0 is supposed to be 1. Here's my formula. I plug 1 into my original formula, 1 plus 1 cubed over 3. And remember, it's just this 1 that's cubed. It's not 1 plus 1 all cubed. It's just this 1 that's cubed. So 1 plus 1 cubed gives me 2. 2 divided by 3 is 0.6 recurring. I then take the 0.6 recurring and I substitute that into the formula. So this was my first iteration. This is my second iteration. So 1 plus 0.6 recurring cubed over 3. This gives me 0.4320. That gets substituted in to give me my third iteration. So 1 plus 0.4320 cubed divided by 3. That spits out my next iteration and so on. And after 5 iterations, I find I've got 0.3474. Now, we're not going to comment at the moment on how good a estimate to the solution of this equation this is. We're not actually going to check it. However, what we can see if we go back to the graph earlier on is that somewhere between 0 and 0.5 there is a solution. And if I look at that, it's certainly between 0.3 and 0.4. So this looks like a fairly decent approximation of the solution. So now we've had a couple of goes at this, it's time for you to have a go yourself. Stop the video, show that there is a solution of x cubed plus x squared minus 5 equals 0 between 1 and 2. Then show how this following iterative formula can be derived from this equation. Note that the last thing you're going to do is cube root all of it. That should tell you the previous line must have said x cubed equals. And then give an approximation to the solution of the equation after 4 iterations. Stop the video now and have a go. Okay, so let's assume you've now got a solution to these three questions. Show that a solution of x cubed plus x squared minus 5 equals 0 lies between 1 and 2. I take y equals x cubed plus x squared minus 5. I substitute in 1 and I substitute in 2, and I find that when x equals 1, y must have been equal to 1 cubed plus 1 squared minus 5. That's 1 plus 1 minus 5, which is minus 3. And I find that when x was 2, y must have been equal to 2 cubed, which is 8, plus 2 squared, which is 4, so 12 minus 5, which is plus 7. I can see the sign change from negative to positive here. Therefore, hence, as the line crosses the x-axis between 0 and 1, that should read 1 and 2 clearly, there must be a solution in this range. So we know that there's a solution between 1 and 2. Show how the following iterative formula can be derived from x cubed plus x squared minus 5. Well, I take the original formula, and I actually know that because I know the form of the final formula, I want it to have a cube root in it. So I'm going to try and get x cubed equals. So my first thing is to take x squared away and add 5, and I do that to both sides. This gives me x cubed equals 5 minus x squared. I cube root everything, and I end up with x equals the cube root of 5 minus x squared. Excellent. Now all I've got to do is turn that into an iterative formula. So my x squared, because it's within the actual formula itself, becomes xn, and the subject of the formula x becomes xn plus 1. And we have our iterative formula. Give an approximation to the solution of the equation after 4 iterations. Here's the formula stated once again. And to begin with, we substitute in x0, which is 1, which gives us 1.5874. This is then substituted in to give us our second iteration. This is then substituted in again to give our third iteration, and so on. And after 4 iterations, you should have 1.4166. You'll notice that I've just added some dots after it to show that it's a continuous decimal, but I haven't in any way rounded it or anything else. So if I now have a look at how valid this solution seems to be, I've taken the trouble to draw a graph of this, and we can see that here would be x equals 1, x equals 1.5 would be on this line. So this is just crossing the x-axis just before x equals 1.5, just below x equals 1.5. So it's fair to say that x equals 1.4 is a fairly good approximation to a solution for this particular equation. Limitations. The great thing, of course, about iteration is you can solve cubics with it. However, the major problem with it, in my view, or the major limitation of it, is that if you want to find this solution here, solution B, then the iterative formula that we employed earlier in example 2 works really well. However, this iterative formula will not produce a solution if you want root A or root C. You have to use this different iterative formula, and you could try rearranging this to get this iterative formula. That's possible, and you could have some fun doing that. But if you want solution A, then you have to use this iterative formula, and you have to start with an x0 value which is less than the value of B, so anything from the left of B. Whereas if you want to get a value for C, you use this iterative formula, but you start with an x0 value which is greater than the value of B. So the thing is, you don't know which solution you're going to get from which iterative formula necessarily, and that's a major disadvantage, major limitation of iteration. And the final thing then is, why learn iteration in the first place? The great thing about iteration is that computers can work with it. In computing terms, iteration is looping. So you can build a loop with some function or equation, and you can use that to generate solutions to an equation or to a problem. So the process of iteration is the way in which computers actually calculate, and that's the reason that it's taught now at GCSE Maths. So we've learned the definition of iteration. Iteration is simply a repeating process that uses one answer, one approximation to a solution to an equation to generate a better approximation to a solution. We've learned how to derive an iterative formula by rearrangement. We've been able to determine whether there is a root between two particular x values by looking at the change in the y value from positive to negative or negative to positive. We've been able to use an iterative formula to find a solution to a cubic function. We know the limitations, which is that you may have to use more than one iterative formula if you want to find all the roots of a cubic. And we've learned that the major reason for learning this is computing and computer science. Thank you for visiting MylesMaths. Please come back soon.